Okay, there we are for our exercise. In case you skipped the previous video concerning infrastructure and tooling, let me say hi, welcome to tutorial 1. And should you have watched your way all through the initial video, then welcome back. It's really time to now look at this first exercise. And I was creating my own local copy of that, where I will start with basically building up the tutorial. So don't be surprised that my notebook looks a little bit different. In the end, it should look similar to the one online. I will just build it up piece by piece, at least in the beginning. That is my idea here. And as I said, if you haven't found the other notebook, it's available on GitHub, and the infrastructural video O, so to say, that tells you in detail how you can get the demo files and the notebook of exercise 1. Which should look somewhat like shown here. And my local copy ends right away here. I just left the introductory pieces in the file, and we'll start from there. And I invite you, of course, to read through all this material, which was carefully developed by my assistants to tell you many details and share a lot of important information. Working with a Jupyter notebook, that's the first part. We have already seen that a little bit, but here we can revisit that. And importantly, you'll find some prominent shortcuts here. If you start working with Jupyter notebooks, just using the commands that you have here in the menu and also the shortcuts here will be okay, but you will realize rather soon that's not the most efficient way. For common commands, you want to know the keyboard shortcuts just to be more efficient when working with your notebook. And some particularly popular shortcuts are here: to copy cell, or to insert a new cell above or below, or further down to change the type of a cell from markup to code or code to markup. And there are a lot more, and bit by bit you can learn yourself through these keywords. I have to say that the way to make use of them is slightly different between your own Jupyter notebook. If you work in the mode I'm showing here, installing the software and running the notebook in your own Jupyter server, compared to Colab. For example, you see this shortcut here that allows you to enter a new cell right below the current one. I have highlighted at the moment this text cell working with a Jupyter notebook, which is apparent from the blue highlighting here. And then this is the command mode. I cannot edit the cell right now. So now everything I key in, it will be interpreted as a shortcut, as a keyboard command. So if I now click B for below, then you get a new cell right below that one. A new code cell, that is the default. And if you rather want to have a new markdown cell below, then you could change that. I'm still in command mode. Note the blue coloring here in that cell. So just typing M should basically change the type of the cell to markdown. And I would first need to type enter. And now blue was just changing to green. I can basically do my changes here. This is a new markdown cell added via a shortcut. Yay, hey. And then shift enter onto the next cell. I can also use the keyboard arrows. They are convenient to browse through the different pieces of your notebook. And for example, since by browsing through my notebook with the keyboard arrows, I'm here still in command mode, I could also use the shortcut D, which is to delete the current cell. You want to be a bit careful with that shortcut, right? But this is a new markdown cell added via a shortcut. It's not critical information, so D and it will go away. There we are. And if you are curious what other shortcuts exist, you can just click H for help, I believe, and then you get a list with all the keyboard shortcuts, and you see there are loads of them. And these are the shortcuts that you can use in command mode on the left. When the cell is blue, highlighted in blue. For instance, we have here changed cell to code, Y, changed cell to markdown, M. These ones we saw in action before. Change the heading. And there are some more shortcuts that work when you are in edit mode, when you're working with a cell. For instance, you're working with a code file, you've written some code, and then you want to split that code into two pieces. That's very useful. Cut selected cells, the X. That's quite useful, as you shall see. And the commands in Colab are similar, just that instead of just hitting the key, like the H in command mode to bring up this window with keyboard shortcuts, you need to press Control M and then the shortcut. Well, basically, this implies that it is in your interest, I believe, especially in the beginning, to really make a choice. Do I use one tool or the other? I think I have a Colab somewhere open. Yeah, here's a Google Collaboratory. So if I just find myself in the command mode here, the cell is highlighted right now. I'm in command mode. Let's go here. I'm pressing H, nothing happens. And now I'm pressing Control and M and H, well, on the risk of breaking my fingers here. And there is the list with keyboards in Google Colab. You will get used to that. Okay, back to the exercise. We talked about cell types. Here is the functionality demo with Y and M. I can beautifully change between the cell types. And I think that's enough for now. You'll get used to it. Concerning Python, it's quite similar to R. It's a bit more object-oriented. We will have to deal and cope more with mechanisms that we find in object-oriented programming languages like Java, more than R. But still, in many settings, Python will just behave as R. The syntax is a little bit different, but you'll get used to that. So provided that you're good in R from business, analytics, and data science, you'll be fine. What you also know from R is that when you want to store some data in the memory of your machine, you need a variable, and you do not need to type variables. By type, I mean you do not need to specify what is the data type of a variable. So if you have a text variable to store some text, you do not need to say this variable is of the data type text. Typing, as they say in programming jargon, is done automatically for you. More recent guidelines that came out for Python encourage you to explicitly state the type of data type that you are using. I believe that is a good idea. Personally, I like typed languages like Java, where everything is very explicit. But for now, we will not make use of that. To simplify my code, I will just rely on this ability of Python to figure out types pretty much automatically. We've got numbers as data types and strings for text. And very important are the data structures to store a bunch of numbers or text. So collections like lists we've got, dictionaries, which are key and value stores, and also tuples. And then there are more data types, and we will introduce these while we go along. Let's start with some of the basic ones. I'll just add a new cell here. That's a coding cell. So we can start with revisiting the previous example. This is just a variable, which I set to 5. And Python will figure out the data type of that variable. And we can check that by just type X. That will tell me what type is that variable. Let's run that by clicking Control and Enter. And Python has established that that actually should be an integer. And if we have another variable y and assign it some text, when it comes to text, it is your choice whether you want to use single quotes or double quotes. I'm using single quotes here. Type y. So y is of type string. That's pretty simple, I believe. How about these elementary data types? That so far is quite simple. How about a list? Lists are important because we will work with vectors and matrices a lot. Let's define a list, and I can also reuse the symbol x. Reusing x, I will basically override the variable. Oh, apologies, I realized that this is very hard to read. Sorry for that. I will not redo everything because you have the notebook available, and from now on I will change the resolution. That should make it much easier for you to follow what's going on and also, well, see in the video what I'm typing here. So let's say we have a list. We need the square brackets in order to indicate that this data type here is a list. 1, 2, 3, 4 is my example. We define a list, or we could consider that a vector that has these 4 elements. And of course, we can print it out and then get the corresponding result. We can print out the type of X, which should be a list. Yep, class list. Oh, be careful here, class. It says class, so that's actually an indication that the data type list internally is stored as an object from the class list. If you haven't done any object-oriented programming before, maybe for now it's okay to just ignore what I'm saying. If you have taken my Java course, that would be a very good preparation. And well, as said, if not, and object-oriented programming, object classes, all that is new to you, I will not have the time to introduce that. Just check whether you feel you need to work a little bit on that to understand everything a little bit better. Then probably one more or less careful read through the Wikipedia page on object-oriented programming is all you need for this course, but just decide for yourself whether you find that's relevant. Okay, so that was our first list. We can consider that a vector. And when we have a list, then what we typically want to do is we want to do some indexing. To pull out specific parts of the list. That is an operation that we will need very, very often. And we could also use the square brackets for indexing. That is pretty similar to R. And what you also know from R is the syntax, where you use the colon to say, give me all the elements from position 1 to position 3. Let's see what happens. Oh, and that is the first surprise. And that's going to be a little bit painful for you in the beginning, I believe. The indexing differs from the way it works in R, and it differs from the way it works in several other programming languages in 2 ways. One is that in Python, it's more computer science-y, meaning that we start counting from 0, not from 1, as we do in R. The first element in a list does not have the index 1 in Python, it has the index 0. If my list is 1, 2, and 3, and 4, and I want to extract the very first value stored in that list, I need to say x0. And then I get the 1 out of it. That's not too common. In fact, most programming languages start indexing from 0, and R is the exception, the outlier. What I personally found a little bit difficult at the beginning is that if you have this index for running from 1 to position 3, so you would expect to have, now that we understood that indexing start at 0, so we would expect to get the 2, that's position 1, and the 3, which is stored at position 2, and the 4, which is stored at position 4, right? That would be a plausible expectation, in my opinion. But in fact, that's not the case, as we see. If we use that index 1:3, what we get is the result 2 and 3. We get a list with only these two elements, 2 and 3. And that shows us that when we index up to a certain point, like point 3 in this example, this last point, the end of the list, is not included in our result. Well, that was a tough one for me, I have to say, but it turns out that it's a quite convenient feature, and we'll see that later in exercises when we work ourselves through lists processing batches of elements, using the term batch here. If you are already ahead with the lecture videos, you know what the term batch might indicate, otherwise don't worry. When we process a bunch of numbers in batches, that way of indexing to not include the last element turns out to be quite convenient. You'll see that, but in the beginning, you just have to keep track of that. And well, honestly, you will make many mistakes, but that's fine. That happens to everyone, I believe. Okay, so let's move on a little bit. We have seen basic indexing. Using this syntax, the squared brackets, and then giving the range of indices that we want to continue with. We can also index from the right-hand side using a minus, so x0, x of 0, does that make sense? Well, first element of x, let's say, is 1. Yep, we know that. But we could also say, give me x of -1, and that's the last element, the 4. Very useful that we can also index from the right, but obviously we can't say -0. Well, maybe not obviously, but that is, we can't say -0. This bit Python will not understand, or rather it will ignore the minus and give me the 1 as the first element. So the counting of the index works a little bit differently when we use the minus. -1 means the last element in the list, and -2 means the second to last element in the list. And well, we could index in this way from -2 to -1. But again, then the last one would not be included. So it's a little bit complicated in the beginning, and you will need to debug your code a lot in order to make sure that when you define more complicated indices, that they will work out just the way you want them. And lastly, you can also delete elements. Obviously, you couldn't say, let's say, x of -2 is equal to 0. I mean, you could say that, but this will not delete the second to the last element in the list. You will just change its value. After performing that operation, your list will have changed and now store the values 1, 2, 0, and 4. And let's say you wanted to, this is not deleting an element. Let's say that was your intention element. You would need to use the command del, and then we can say del x -2. And then it really goes away. Print x. And now there goes the previously third element. It's gone by now. And our new list after the deletion has only 3 elements left. That's maybe also noteworthy that in Python, oftenly when we change something, it's changed in memory. So this operation has changed x. And we need to be a bit careful that commands or operations that we perform to our data can change the data. If we want to copy the data and then make a change to the copy, we need to do this explicitly. And the next example is to show how that works, where we will basically create let's recreate X for the beginning. So let me recreate X. Then I introduce a variable Y, which I assign the value stored in X. And then I'll make a change to the variable Y. Putting a 9 into the very first position. I change Y, and now I print X. We can also print Y, but printing Y is not so interesting, I believe. And you see they both are the same, which implies that by changing Y, I have also made a change to X. Because this Y equal to X does not create a copy of X. What is copied here is simply the memory address where the data in X is stored. And because of that, Y and X are now tied together, and every change I make to one is reflected in the other. And let's introduce a new variable Z. And with this syntax here, this colon says, give me all, give me the whole X, give me all the elements in X. That tells Python that I want that to be a copy of X, or more specifically of the data stored in X. So if we make the change to Z as well, setting the very first element to 9, or let's say to 8, and print everything out, let me deactivate this statement. I think the result will be clearer. You have seen that before. Now we're doing that with that. And here you see that I'm assigning that the values of X. That's the key difference. I'm assigning X set the values of that. And this way, Z and X are not tied together. I take all the data stored in X, copy that data to a new place in my computer memory, and that place I can thereafter access using the variable Z. But if I want this copy, I need to make the copy explicitly. If I don't make the copy explicitly, the variables like X and Y are chained together, and changing one of them will change the other. All right. Now that we've seen some basic data manipulation in Python, let's move on with functions and methods. You remember them from R. Functions come in two flavors. On the one hand, you can download packages that provide a lot of functionality in the form of functions. For example, in Embed, we've downloaded a package random forest, and we were then, after downloading and installing that package, able to run the random forest ensemble algorithm on our own data by just calling a corresponding function. And that works alike in Python. And also, as we've seen in R, we can write our own functions that will then encapsulate some functionality that we need in our program. Let's have a look how that works in Python. In fact, we already saw or got a glimpse of some functions in previous examples. Let's now revisit them. So first of all, let me create a new cell here, creating a little header, functions and methods, and why and methods, and what's the difference between the two. We'll clarify once we go along. Previously, we had our list X, and we have discussed how X can be copied and how we need to do that explicitly. And we have also seen how X actually is of a data type list. Remember X, here's X again. We made that a list. We have then queried the type of X to learn that it is an object of class list. And whenever you work with objects that correspond to some general template, the class is the template, and an object is a concrete example of that template of that class. And whenever we work with objects and classes, it is common that these objects can do certain things, that they can perform certain operations. So X actually is already able to perform certain functions without us knowing. And to get a feeling for the abilities of X, our object of type list, let's type X and then the dot. That's basically the syntax that says, so I have my object X, and now I want to call a function on that object that applies to that object. And if you hit the tab key on your keyboard, you will get a tooltip of the functions that could now be invoked, of the type of function that X offers you. And you have append here, you have clear. Interestingly, you also have copy, which is exactly what we used before, just in a different, using a different type of syntax. If we call the copy function, then we can make a shallow copy of X, meaning that we afterwards are able to manipulate the variable Z as we did above without affecting X. That is just another way. So above is the same as that equal X. And that's the statement that we've seen before, where we basically, with this syntax, we go over all the values stored in X and ask Python to output all these values. And then this will collect all the values in the variable Z. That's one way of doing it. But we could have also used the function copy, which X offers, because X is an object of the type list, and the type list, that specific class, that template, supports this function to copy lists to other variables. Okay, so copying is one thing that lists can do, but surely they can do a little more than that. And since that is a copy of X, and since X is a list, we would expect that that also is a list. In fact, if you want to double check, you can use type again. So let's double check. Oh yeah, that in fact is a list, very much as X. So we would expect that if we key in that and then dot and then top, and there you go, you also get this nice tooltip of all the functions that are available to you. And why not having a look at the very first one, append? That's actually one of the probably most common functions that you need together with lists that allows us to add certain values. Okay, let's append a value of 1. We had 1, 2, 3, 4, and now we'll append a 1. So maybe print that, then append, then print that again. Surprise, surprise. Nobody would guess what's going to happen next when we run that code. There we are. We get a new one. Easy. What else? That dot, let's check. Pop sounds good. That's a common operation where we basically get the last element out. Let's try pop. That dot pop. Print that. There goes our 1, which was just appended. You basically take the last element lying on the very top of your list. If you imagine that as a stack of numbers or of elements that you put on top of each other, pop takes the last one and removes that. Let's add the 1 again, and now, or maybe one last, there is a nice function count. That's sometimes useful if you imagine you have A variable that stores certain category levels. Let's say you have a variable job status with category levels like self-employed, managing position, data worker, clerical worker, state worker, etc. And you want to count the number of occurrences for each of these category levels. That is where a count can be useful. You might think that the method count allows you to count the number of elements in the list, but it doesn't. Rather, it allows you to count, specific value. And if you look at the help of the function count, you see that you need to key in a value. This function needs an argument. Return the number of occurrences of value. Okay, so we could use this function to find the number of ones stored in that list Z, which is 2. Surprise, surprise. Because we just appended the one. And if we append another one, and maybe one more, wow, by now we have 4 ones. And the list data structure allows us to count these ones. As much as any other number, like the 2, where we have 1 element, or the 82, where we have 0 elements, right? That number does not show up in this list. You got the idea. And in general, since there is so much functionality available, if you're working with a list and you need to perform some operations, I need to explain that abstract. You need to perform some operation and you wonder, how do I do that? Normally, do not try to implement the operation that you need straight away on your own. Probably it's available somewhere, somehow, and probably there is a way for you to make use of that function. So before trying to implement some functionality yourself, let's say adding elements to a list, make sure you did a careful web search whether a ready-made function exists that performs your task or that solves your problems. Normally, it will. And with that, we continue here and move on to another data type other than the list, which is the dictionary. Dictionaries are also important. They are key value stores. You store pairs of data together. And the first part of the pair is the key, say a matriculation number. And the second part is the value, say the name of a student. And then when you work with this data structure, first of all, you can store a set of key value pairs, unlike the list where you store a set of values that are individual or atomar values, like numbers 1 and 2 and 3 and 4, but the 1 and the 2 and the 3 and the 4, they have nothing in common. They just live in the same list. It's different in dictionaries. There we have these tuples, a key and a value. And that we will also need quite often. So let's have a look at how dictionaries work, starting with us defining our own dictionary. To create a dictionary, we need to learn a little bit more syntax. In particular, what you need to tell Python, or the way to tell Python that you're creating a dictionary, is to use the curly brackets. Previously, to define a list, we used the square brackets, right? Move up a little bit. Here was our example to create a list where we had the square brackets and we were then enumerating some numbers. We could have enumerated text as well. The data was enumerated and the square bracket was the delimiter. And with dictionary, slightly different. Here we use the curly bracket. And then we specify our key, which typically is a text. So let's say A. And then we use the colon and specify the value that corresponds to that key. Let's say 2. It's just some data that we basically now integrate into a single data structure. Let's have a second key, B. and give that the value, well, B could also G store some text, and one more, C, there we could store a list of numbers. And if you want to continue, you can have D, where you store a list of text. I think these are pretty much the data types we've seen in action so far. Let's see what happens if we print that. Well, we just get the output of our dictionary where all the keys with their values are printed to the screen. It's not so amazingly interesting, but the use case of a dictionary would be that we know a key and want to pull out the corresponding value. So, for example, I might want to pull out the value of my dictionary for the key B. So then I basically index my dictionary, and as index, I give it the key, and the return will be whatever value corresponds to B. That should be the text cheese here. And there it is. I understand that this dictionary is not useful. It's good for nothing, as they say. But try to follow along and understand the potential of this mechanism, key value store. We'll see it in action, and we will use it a lot. I can promise you that same type of concept applies, for example, when we play with data, where the key might be a column header, and using that column header to access a data structure that stores some data set, we can pull out all the values of a single column. Same idea. That is a dictionary. Nice key value store. Obviously, we can, in the similar way, get also the key for the value for other keys like key D. Then we get our list with text. That's how it works. And while this is clearly the standard use case, putting in a key, getting out the value, there is a little more we can do. We can, for example, also ask the dictionary for a list of keys. Sorry. And then we get A, B, C, D. So now we know all the keys that exist. I could now enumerate over that list and pull out all the values one by one, since I know the key. Equivalently, I could ask my dictionary to give me all the values. Then I also get a list of all the individual values. 2 is the first value, G is the second, this list of 3 numbers, the third, and fourth, the list of my 4 subsequences or 4 text sequences. Keys, values, and last we have dict.items. That's a way to get out the pairs, key and value. The key value pairs, we can get these using the function items. Dictionaries will be very useful for us whenever we need to create our own data structures. For example, imagine the use case of setting up the search grid of meta parameters for some machine learning algorithm. Hope you remember the model selection part from business analytics. You could, for example, set up, and now let's try to do something useful, having a dictionary for tuning random forest. You could create a dictionary called RF grid, random forest grid, and then say, now this is a dictionary where I have mtry. And for mtry, I want to consider settings of 1, 2, 3, and 4, maybe. And you could have a parameter entry, which is another key in this dictionary. And let's say for entry, the number of trees in my random forest, I want to have a list of 10, 100, 500, and 2500. That's a parameter grid which you could consider to tune the random forest machine learning algorithm. And it's here just an example how dictionaries can be useful. Okay, let's move on and talk a little bit about conditions and loops. Conditions and loops appear in every programming languages. They allow us to control the flow of our program, which parts are executed and under which conditions. That is the conditional statement, and the loop allows us to run certain parts of our code multiple times. And Python is no different from other programming languages in how these constructs work. The syntax is a little bit different, but that's about it really. So let's briefly introduce the corresponding syntax. Let's start with the condition. We can create a variable. Let's say x is equal to Python. Or let's say Python. And then we could write a statement where we go if x is equal to Python colon and print, so we program in Python. If we leave it like that, that's basically a statement that will be executed only if the condition is true. Note how I need to put in two equal signs to tell Python that I want to compare two things, the right part and the left part. If you just put one equal sign here, that's not going to work. A comparison is indicated by using two equal signs. We could also add an else part, else print. So we use some other programming language. And well, what's special about Python, not really special, but you need to know about it, is these three parts, these blanks here. They basically tell the Python interpreter where the conditional part is, and that this part here, sorry, is run only if the condition is true. And you don't have any brackets as you would in other programming languages that basically delineate the part that's under the if, so to say. You don't have that in Python. Instead, you have these indentation, these four spaces at the beginning, which tell the programming languages that this is the part that belongs to the if. And is run only if the condition at if is true. Let's try running that. So we use some other programming languages. That, by the way, shows us how the string comparison considers the case, the capitalization. And knowing what we did before, we should basically improve our condition to, first of all, take the variable that we are comparing and then making everything lowercase. If we rerun the code, so we program in Python. That's if and else. This indentation thing is a bit weird at the beginning, I believe, but no matter which programming environment you use, whether you use Colab or a Jupyter Notebook, or whether you maybe prefer using some Python editor like Spider, Visual Studio Code, or PyCharm and do your coding, the editor will typically make sure that everything works for you. if I, for example, want to continue this condition here, so we program in Python, that was already it. If I just hit enter at the end of the line, the cursor is moved to the right position so that I could continue programming statements that come only if the if condition evaluates to true. Like print great, that's a nice sorry, some disturbance of the force. That is a nice language. Here we go. Click run. You see what I was going at. One extension, you know that if typically allows you not only to do yes or no type of comparisons where you have two branches, but you can have multiple. And in Python, you can do so by using the statement elif, where we are allowed to write another condition, x lower equal Java. Mind the colon at the end. You will get a syntax error if you forget that. And then we can have print, okay, so you probably do not do data science. That's a bit unfair. Maybe you do, but anyways, let's see. Java. So you probably do not do data science. Works like a charm. Wonderful. Okay, that was the condition. And assuming that you've done some programming before, that's probably enough. You have seen the syntax. As always, it will take a little while until this syntax really has found its way to your heart and to your routine, and then you naturally make use of it. You will make some errors when you start, and you will have to go back to this tutorial, or you will, which is better, have to ask Google what is, or whatever your favorite search engine is, what's the if condition in Python, and then you'll get some syntax examples and you'll be fine. Let's continue with loops. Loops are these programming statements that you run multiple times, and the most, or at least one very common setting where you want to use a loop is to process all the elements in the list, in a list, one by one. My list equals to 1, 2, 3, 4, and 5, and 6, and 7, and 8. Here's my list, and now I want to process all these elements. Maybe I want to multiply them by 2 and then print them out. That would be a nice use case to write a loop. And there are multiple ways I can do that. One is using a for loop. For the in my list. That is one way to write that down. I have an iterator variable that is v, and I need here after the in, which is an important keyword, after the in, I'll have to specify some data structure that is that can be enumerated, where you can basically loop over which you can do some looping, such as a list. That's one example. That should work. For v in my list, I should be able to say print v by 2. That should give me some output, and here you go. You have all the values in my list multiplied by 2. Just to make sure, obviously this has not changed the values in the variable my list. I haven't touched them. I have pulled them out. They have been assigned to the variable v, iteration per iteration, and this value I multiplied with 2. So I can run my code again and I will get the same result. Oops, sorry about that. And one more time. And here's the result again, and one more time. It's always the same. We could also do some other mathematical operation, but I think this is not so interesting. Let's rather do something else. We could do print v here and then, yeah, as I said. This is just to show in this for loop, obviously I can write as many code as I want to. What else? We were creating these other data structures beforehand, our dictionary, for example, and we could basically make use of that and write a loop, process all the key value pairs in our dictionary. And here comes some specialized syntax, key value in dic items. That's a tough one. There are many syntax constructs that are very convenient, but can be confusing at first glance. And I think this is a good example. Remember, when you use the method items that exist for dictionary objects, remember how this method gives you as its output, well, dictionary items, that looks a bit like a list. It looks a bit like a list in that you have square brackets. That looks very much like a list. And you have elements separated with the comma. That also looks very much like a list. It is a list. Question is, a list of what? Well, let's make sure that is a list. So we use the type function. Type is quite useful because many operations that you want to perform depend on the data type that you expect to work with really being the data type of your data. And type will always help you to debug these type of issues. Okay, so it's not really a list, it actually is a data structure called dictionary items, which is a specialized dictionary output structure. We could, if we are interested, go on the web, try find some more information. But we have seen that there is some result. Why don't we introduce some variable x? Assign the output of dic.items to x. And then because the result looked very much like a list, you can speculate that it should actually be possible to pull out the first element in this result. And it doesn't work. Dic item object is not subscriptable, so it doesn't really work that way. Let me check something. No, it doesn't work either. Sorry about this little detour here. I wanted to debug that statement, but that failed. Apologies. The thing is that what you get from dictionary.items is a kind of list of tuples. We haven't introduced tuples before. Tuples are a data type that, unlike a list, can not be changed and only be processed. This syntax will essentially, let's have a look at dic items one more time. Sorry, I need to slow down. We will get, first of all, this bit as output. We do get that, and I was trying to pull that out explicitly with my indexing, but apparently that's not allowed. We will first get this output. And then when we enumerate the dictionary items, in the second iteration, we get that output. And these are then called tuples. And I can basically split up that tuples into its individual parts with the syntax for key, comma, value, the result will be that in the first iteration of my loop, I get this tuple, and then the value a will be assigned to the variable key, and the value 2 will be assigned to a value. And that allows me to do something with my list items. So I could, for example, do some printing, print the key and these curly brackets in a text allow me to basically inject some variables into my output. I use the function format, which implicitly you have seen before. Format is a function that exists for text. That is a text. Text.format. The text is an object of the type of the type string. That type knows the formatting function, and if I now enter here key and value, the values that are currently stored in these variables key and value will be injected in their order into the parts where I have the curly brackets here in my text. So this is the first curly bracket. The value of the first variable, which is key, will be inserted into here. And since I put that into a loop, the first iteration of my loop will have as key and value a and 2. The second iteration of my loop will have as key and value b and cheese, and so forth. There you go. Again, it's a trivial or pointless example. That code does not do anything useful. It's all about introducing some syntax that you will see often and need often. I know it's quite a lot, but we can't help that. You will need to do a little bit of practicing here to really internalize these bits. The for loop also is used in an abbreviated way. There's also a while loop, but I'll leave you to the notebook on GitHub, which shows you how the while loop works. It's quite straightforward. And rather, I want to show you something else. Let's say we have a list of numbers. I'm copying so that you can easier follow along. Let's say we have a list of numbers here. And let's say you want to do some operations with that. Here is a syntactic construct that you see quite often. X times 2 for X in my list. That's also a construct that I found rather weird when starting to do Python. You have a for loop for X in my list that goes over all the elements in that list. And then you basically, in the same line of code, you perform an operation with X, namely X times 2. So that is a lot of what's a lot of logic that's happening here in just a single line. And running that, you get the results. It's the same as we had before. You basically just multiply every element of my list with 2. That's the easy part. But from a programming perspective, that's not so nice. It would be a lot more explicit and easier to understand had we written that like for X in my list, X is equal to X times 2, print X. That's just the same, but it does so, in my opinion, a lot more explicit. It's a lot clearer, this code, compared to that code. The other code is a lot more compact though. And I wanted to bring that up once because we will see it a lot. And if you go on platforms like Toward Data Science, look for data science blogs at Medium, or wherever you look for additional material, also if you follow all the links that I provide in my lectures, this very condensed version of for loops is used a lot. So you have to make your peace with it, whether you like it or not. All right. Next on our agenda, we have functions. Our own functions. We already used functions, but as I was saying, we can also write our own functions. Let's also have a look at the corresponding syntax. A function always starts with the statement def. Okay, so here's def. Just I'm defining now my own function. My function. And we have the possibility to specify a bunch of arguments that our function receives. For instance, we can specify two arguments, a and b. We need the colon once again to basically say that the header of my function is over. And then we can basically implement that function. And it's good practice to document what a function is doing, provide some documentation. And for that bit, well, you can also use the single colons here. The syntax are these three double colons or single colons. Here is the documentation of my function. You could, for instance, spend a little bit of time to explain the inputs and the outputs to that function, that you have the variables a and b here, for example. Where you could say in a scalar value, in b scalar value, out the product of a and b. That's just documentation. The implementation of your function could go here. Let's make it easy. Result equals a or b. And in Python, you also need to explicitly return something from a function. If you want to return something, return result. And that is it. That's our function. And we can call our function just by its name. So we could say my function 5 and 3. And we would expect to see as a result the value of 15. And we do. And we should also be able to ask for the documentation, which we spend so much time on providing. Signature, my function AB, docstring, here is the documentation of my function. Scrolling a little bit down, I could basically get the rest. So the documentation is to help others keep track of what your function is doing, and also for yourself to make sure that you understand when you come back a week later what your functions are doing. All right. At this point, I would like to stop with rebuilding the exercise notebook that we have available. Up till here I did with minor adjustment, but basically all we did so far is also part of the exercises. And instead I want to switch to the exercise notebook, because at this point it would become a little bit unhandy to write everything. Essentially, in the notebook that corresponds to the exercises, we are at this point where there is an example that might be a bit tough for all of you who have never seen some object-oriented programming before, because we are designing our own class using the keyword class. You have seen the class list in action that comes with Python and provides methods like count, like copy, or like append. And you have also seen the class string in action, and you have created objects of that class by creating string variables, onto which you could then apply the methods upper, lower, or format, or others. That is nice. That's nice that you can use these inbuilt classes and create objects of these classes, but Python also allows you to create your own classes to extend functionality where needed. And well, although we don't have time to go into the details of object-oriented programming, to give you some intuition, when you need a certain data structure that stores data which is somehow related and that also offers some functionality to apply on that data, like the class string that allows you to store text data and apply some functionality on that text data, like upper or lower or format, right? Whenever you have something yourself, a setting where you need something like that, but there is no predefined class, you can write your own class. And this is also the example. We are creating a class person, which is meant to store data of people. That is the idea. And then we just note this keyword class. We give our class a name, person. We use the colon again to basically enter the implementation part of our class. Here is some documentation, class person for human interaction. And here we use ourselves these two underscores for a method name. I was saying earlier on, that is a way to, it's a convention that class methods call or name their methods in this format. I'm very rough here because I really don't want to go into details. It's just a method that we need for the class. In it, it is called have you done NLP, OOP, you know what a constructor is. That's the way how to define a constructor in Python. That is just a method that is executed anytime an object, an instance of the class is created. And we have the keyword self, which is a self-reference. The reference points to the current memory location where the object we are creating is stored. And then we have some other arguments that go into these functions, name and age. And you also see how you can assign default values for certain function arguments by just putting the default value into the header of the function. The implementation part we have seen, documentation. And this bit here, we use this reference self, which basically points to the object itself. And then we use the .no syntax, .name, .age. This is basically specifying that our object knows two variables that are called name and age. And we are assigning some values to these variables, namely the values name and age that came into the function here as arguments. And then we implement some methods, happy birthday, which just prints happy birthday to the screen, and greetings that just prints another nonsense message to the screen. And the only notable thing about these methods is that we use the data, namely self.name and also here self.name. The data is stored as part of the object, and we can access this data in the object's methods. We can work with that. That's the idea. A class is a combination of data that lives in variables like name and age, and methods that work with that data, like happy birthday, where we need the name to print it out, but where we also increment the age of the person. and adding 1 to it. That's the shorthand form for self.age is self.age plus 1. I don't quite remember whether this shorthand form also exists in R. I think it does, but well, it's generally just a very common way of simplifying notation in programming languages. Other than that, the implementation is not particularly interesting. Oh, well, should you stumble upon this, that is an artifact. Older versions of Python used this syntax where you have a string and then put an F in front of the string to basically tell Python that in this string you'll do some formatting, or you want Python to do some formatting for you. It's an ancient way of writing it. You shouldn't make use of it. You rather should use the version that you see above here with string.format. So let me correct that right away. I should have written that in this way. Dot format self age. That also gives you a cleaner separation of the text part, which is this bit, and the data part, where you inject the value of certain variables into your text, which comes after the format. That is a class, and well, I need to run this code so that this class is made known to my notebook, known to Python. Let's run this. Done. Somehow my notebook keeps getting changed. Ignore that. You shouldn't experience that behavior. It has to do with the way I set up my infrastructure here. Not to worry. Look at this code. We are creating a variable example and assign it the result of a call to person. Person is our class. And as arguments, we are putting in the values Johannes for name, which is the first argument, and the value 20 for age. And writing it like that, the constructor, that's just the name of this method that's always invoked when you create an object, is run, and it receives here a value for the argument name, Johannes, and another value for the argument age, which is 20. And then we have this object, and we can use it, and we can, for instance, call methods on it, like here, example.greetings. So that invokes the greetings method. Or we should also be able to work with the data stored in that object. So for example, we should be able to query the name of that exemplary person to get the result, Johannes. I have access to both the variables and the methods. That's, by the way, not proper object-oriented programming. It's quite the opposite of that, but this is a data science course, not an OOP course, so we don't want to go there. Indeed, we don't want to go there. Okay, right. That was like that. Greetings. Greeting, not greetings. And just to illustrate this relationship between the object and the class, let's create another object. Let's call that second person. Let's call that Stefan. And let's say 45. Here we go. And basically what I'm trying to show, we use the same class, the same template, person, but now we have a second object, second person, that belongs to that class, but has its own data. So if I say You see here how the value of the variable name stored in that second object is Stefan, is different from the other one, Johannes. And the last example would invoke the happy birthday method for Johannes, or my first object, and thereby the value of its variable age gets changed to 21. You see it here, but you also see it here. And this has no effect whatsoever on the age of my other object that remained unchanged at 45 until we increment that by calling happy birthday or manipulating the variable. All right, that's that part. Now let's have a quick look into libraries and packages. That is how you extend your Python environment and allow yourself to make use of all the standard libraries that exist and are available for us. And the notebook provides some more brief intro into your options here. What are recommended options to install packages from the web? Have you installed Anaconda? Well, have you used Google Colab? And you do not need to worry for now. Have you installed Anaconda? You will, for now, have all the packages already installed on your computer, so it's enough to load them. Later on, the situation might emerge and will emerge that you need to first download and install a package from the web before you can use it in your code. There are, again, multiple options how to do that. You can do it on the fly as part of a Jupyter Notebook using this third option here, install in Jupyter Notebook. And then you would need this syntax here if you use pip, which is basically the other very common package manager, or using Conda if you use Anaconda. Neither of these options is really recommended. The best option, although it involves a little bit of work at the beginning, is to install every library that you need, every module that you need using GitHub. Using Anaconda. Anaconda will make that library part of your environment, of your sandbox. And then you can use this sandbox and work in your notebook with all the packages that exist in your sandbox. That's by far the best way to keep track of all the libraries and their versioning and ensure that you do not crash your code by installing an update of some library. But as I said, it requires that you spend, let's say, half an hour or so to familiarize yourself with Anaconda and the way in which it manages packages and in which you can create your own packages. Likewise, if you prefer to use the pip, then Anaconda, same story here. You need to invest a little time to familiarize yourself with how that works, but you will benefit from that. Here is a demo how you could install things on the fly. I won't do that because, as I said, it's possible, but it's not the option I would recommend. And the packages that we will get to see first are Numpy for numeric manipulation, linear algebra, Pandas for data management. The Pandas library provides something like a data frame. You might remember that the data frame was our common way or common structure to store tabular data in beds, data frame or data table. In Python, luckily, we do not need to make a choice because there only is this data frame is by far the most common one. It's nice. I would say it's as easy to use as the data frame, but as powerful as the data table. Some people might disagree with that. For us, at least, it has all we need. So the Pandas data frame, that's going to be our main type of class to process data, or just elementary Numpy matrices or tensors. for later parts of the tutorial when we do deep learning, often data is stored or must be stored simply as a matrix or as a tensor using Numpy. That's fine. Then we have matplotlib and Seaborn, these library I was mentioning earlier in the introductory tutorial that help us with plotting. And then there is scikit-learn, which is the go-to library for vanilla machine learning. All that we did in bats, you have available in scikit-learn. We'll see it in a subsequent tutorial, just to remind us. If you have installed a package, you can import it. And you see the examples here. This will run on your machine only if the packages Numpy, Pandas, Matplotlib, and Seaborn are available on your computer. Have they not been installed before, this will not run because these libraries that you're trying to import will not be known to Python. If you use Anaconda, all this is installed by default, so you do not need to worry. It's common practice to introduce upon an import of a library a prefix using the statement as np, and that prefix allows me in the following to call all the functions that exists in this Numpy library by writing np dot. Let me run this so that all the libraries get imported. Here we go. That's not strictly needed. We import it again. We are designing a Python list here, our list. That's just ordinary Python. And then we convert that list into a Numpy array. Yeah, the list is a data structure that exists in Python. And Numpy has its own data structure and data structures, one of which is the array. A Numpy array allows you pretty much what a Python list allows you to do, but it's somewhat different as well. So that's a little bit annoying that there is maybe not the type of standard data structure, and you just need to make sure that you can cope with multiple ones. Pandas data frames are super important. Numpy arrays are super important as well. But the elementary Python data structures are also important. So you need to make your peace with all of these. We have imported Numpy before. Okay, so I should be able, after running that code, I'll create my list here. I also should be able to type np dot tap to then get my tooltip of all the functions that I have access to in this library, in this Numpy library. That was why we loaded it in that way, import Numpy as np. And you could have used a different prefix. Instead of np, you could have picked whatever you like better. But for standard libraries like Numpy, Pandas, etc., there are these standard prefixes, and you really should use them as well to ensure that your code is easily understood by others. And just scrolling through that list, there is a lot. So that is a function-rich library with loads and loads of functions and data types and classes that live in there. And we will not go through all of that. We won't even get close to going through all of that. It's just some basic functionality that we will have the time to look into. It's the go-to library for algebra, linear algebra in Python. And the first thing what we do with this library is we're creating a Numpy array, which we can do as one example how to create a corresponding array by just putting in a Python list and sort of converting that into an array. Numpy or np.array allows to create an array. And there are different ways to do so. We can ask the help system. Remember, I was just pressing Shift and Top. Array. Okay, that's the function array. We put in some object, could be anything. We can specify the data type of that, but we don't have to. Whether we want a copy, whether we want a certain ordering, etc., creates an array. So, well, it's moderately helpful, let's say. One way to create an array is just inputting a list. That's the way we took here. And afterwards, we can just, with that array, now we just get this array. But the point is a Numpy array allows us to do more than an ordinary Python list. If I use my Python list, our list dot, I can append items, I can clear the list, I can copy it, I can count certain occurrences of elements in that list, I can index it, insert something, pop and remove, and sort it, but that's what I can do. And that's a little different if we, let's say, we store that Numpy array in our variable x. Obviously, x now has this value, but with x, I can do a lot more. That is, for us, could be the point to create a Numpy array as opposed to just working with a Python list. If we have numeric data and when we want to do something with it, it's much more powerful to work with a Numpy array that allows us to use all these many functions than using a basic Python list. We get additional functionality. That's the point. And you see some of that functionality here, where we use the square root function, or where we use some other mathematical function like the exponential function, and how Numpy allows us to basically apply that to the list in one go. It's not, well, particularly remarkable. We just feed in a list and then apply some mathematical operation on each element of the list. Here we use our lists. Of course, I could change it with x and apply all of that to my Numpy array. It gives me the same result. And also, I think I could invoke the function square root right on my Numpy array. That should also give me the same, damn it, I'm always overestimating the abilities of Python. It doesn't work like that. What's the problem here? Square root is not implemented as a method that I can invoke on instances, on objects, like x is an object of the class Numpy array. It's rather implemented as a static method that I can only invoke over the class prefix here, Numpy. But of course I can give it x as input data. Sorry for the confusion. Sometimes that sort of works, sometimes it doesn't. I should have checked earlier on. I didn't. Anyways, it is just illustrating us here how we can use Numpy functionality to work with our data. Here we create a multidimensional array. In fundamental programming courses, this is already fairly advanced data structure, a list of a list. Each element in that list is a list in its own right. You see that by keeping track of the squared brackets. And you can also use the function len to count the number of elements in the list. And if you apply that to list of lists, the count is 3. And if you apply that to the first element in that list, that's also 3, because it's the list of a list, and the inner list also has 3 elements. If we add 1 element, then the count raises to 3. Whereas the list the outer list, so to say, it still has 3 elements, right? I know. That's a bit complicated at first glance. The thing is, we need that a lot because a list of a list, that's actually a matrix, if you think about it. Not this way, but now I essentially have a data structure with numbers from 1 to 9. And you could think of that as a matrix where I have 3 rows, 1, 2, 3, 4, 5, 6, 7, 8, 9. Or you can think of it as a column matrix. And that is really how we will put data into neural networks when we start working with deep learning libraries. And this is why we need to get accustomed to this multi-dimensional list. Here I have a list of a list, which is a matrix, but it could be worse than that. So on the risk of losing everybody, we could do also something like 1, 2, and 3. 4, 5, and 6. And now I have a list of a list of a list. That's a weird data structure, but now I have, so to say, created a tensor with 3 dimensions. Just that for now, the 3rd dimension, I haven't put any data in there, but I wanted to show that the number of dimensions that you have in this multi-dimensional array is not constrained to only 2. You can have more if you wish. In the reminder, you see some common Numpy functions that we will use a lot. We can create an array out of our list of lists. The most basic data type for neural networks is an array of lists. You have the function arrange, which will give you a sequence of numbers in a certain interval. You see how it arranges the numbers from 0 to 10. That's convenient if you need to specify, if you need to configure a for loop and you want that loop to run for 5 times and count from 1 to 5 in that loop. Numpy arrange would allow you to generate these numbers. You can generate identity matrices or also matrices full of zeros of certain dimensionality. Oh, sorry, I was skipping one here. You could also specify the increment in a range. You can generate identity matrices using the command 1. If I change that to 3 by 3, I get a 3 by 3 identity matrix. I can use zeros when I have a matrix full of zeros of certain dimensionality. That was, by the way, sorry, that's not, that was a matrix full of ones. And then if I want the identity matrix, I use the command I. I have it later. That gives me an identity matrix. Sorry, I was slightly lost earlier on. Apologies. But it's good. Probably me making errors. Make sure that you are still awake. And or maybe it's then a little bit less frustrating if you write code and it doesn't work at all. You see, the same happened for me. Okay, once. And if I run this code, it will give me another error. There we go. At least I was telling you earlier on. Yeah, the reason is that the function once expects a certain type of input. And that input that is expected is different from the function I was using earlier on. If I put I here, my code was working just fine. And looking at the docked string, the function I, numpy.I, expects a number n and another number m. Returns a 2D array with ones in the diagonal and zeros elsewhere. And If my goal is to create an identity matrix, one dimension is maybe enough because I could simply assume that if you don't enter a second dimension, well, you just have that many elements, right? But more importantly, for once, I need to specify the shape. That's my first argument. I need to give Numpy information on the shape that I want. And shape, that refers to a tuple. I need to input a tuple that specifies the shape of my data. And a tuple in Python, well, that's a tuple. That bit here is a tuple. It's a tuple, two numbers, 3 and 3. Once assumes as its first argument a tuple. So I have to call the function in that way. Then it works. Here's also the identity matrix, and you see you don't actually need that M. If you call it with a 6, you just have that many elements. An identity matrix is always a square matrix, so you just need to know the number of one dimension, and the other must just be the same. Line space, another handy function, evenly spaced numbers in a specified interval. I'm just running over these functions because I know that you can't memorize all of them by just watching this video. It's impossible. It's just a way to introduce a bunch of functions. Line space is useful for plotting. If you want to create a plot of some function, we could generate input data. Let's say we have a function, y equals to f of x. We could generate input data x for that function using line space, which just gives us 10 evenly spaced numbers in the interval 0 to 5. Since Numpy is used very often in the context of working with matrices and vectors, in other words, sequences of data, you can also index Numpy arrays. And the indexing works pretty much as it does with lists. Let's look at this example here. We use the function arrange, Numpy arrange 0 to 20. Remember that this is going to give us a sequence of numbers from 0 to 20. Let me briefly deactivate the middle bit. Here's our sequence. And then the bit I just uncommented will essentially just change the value of the position. Do you remember which position that will be? So we start right at the beginning with the 0, and then we will change the first 5 elements, right? 0, 1, 2, 3, and 4. The 5 will not be considered. The last element is that -1, right? We discussed that before. Let's see. So 0, 1, 2, 3, and 4 will get set to the value of 0 by that code. That's the way Python indexing works. And 5, 6, 7, they remain unchanged. We can also extract the data from an array, as you see here. So we extract the first zeros. That's now a slice of that array. And all element of that array we here change now to the value 999. And we see the same phenomenon that we had earlier on, that the slice of an array, it's not a copy. The original array now has also changed. So the behavior of lists that we had earlier on with X and Z and Y also generalizes when we work with arrays, with Numpy arrays. Unless we explicitly copy an array, we don't get a copy. But we can explicitly copy an array using the copy function, which I was also introducing earlier on. So that works equally, and then just changing the value in the variable slice of array is not going to change the underlying array. So let's make this copy here. Now we copied the 4 values, which currently are 999. Let's set them once more to 0 and see what has happened to the array. And unsurprisingly, the array hasn't changed. Okay. You also, in addition to numeric indices, have R-like means of logical indexing, where you can get all the elements in the array that are greater to some threshold. You index your array with a logical expression. Let's run that. So we have the 99, 999s, and we have 11, 12, and so forth, all the way to 19. Well, we don't have the 5, 4, the 5, the 6, the 7, the 8, the 10, the 9. We don't have these due to our logical indexing. That works as in R, and as always, indexing, we use square brackets. If you want to generate random numbers, Numpy is also the library which you will probably use. And here are some examples. Random numbers in a certain interval, we can generate that. Well, the input that we gave in here, 2 and 4, give us the dimensionality of the random matrix that came out of that, or if I call it like that, that's going to be a matrix. You can invoke that with any number of input arguments. And if you want to have a 3-dimensional tensor with random numbers, you could just extend this call to rand n, and your data will change accordingly. It will take you a little time to know the signature. This is how they call it, the signature of the method that you really need to use and will use quite often. Once you've used this method a couple of times, that will be natural to you. Random integer numbers, there is random int, and you can basically give the range random integer numbers between a value of 1 and a value of 100 and 5 of these, or 15 of these, or 15 in the range 1 to 10. Obviously, there will now be some repetition, right? Okay, well, a bunch of more functions. The maximum you can compute over an array. That one is, let me run that. That one is quite important, reshaping. In neural networks, we will often have to reshape data to ensure that matrix multiplications really work out. In the easiest way, in the easiest case, it will be enough to transpose our data, but that is not always enough. Sometimes we really have to reshape our data a little bit, and that is where reshape comes in handy. I have this matrix here, ARR, which stores the numbers from 0 to 24. So it has 25 numbers. And currently, it's basically a vector. It's a one-dimensional array. And I can now reshape that into a two-dimensional array with 5 by 5 dimensions. And by default, you see that this array is created, let's say, in a row-wise manner. I first take the first 5 values, and then for the next row, I continue with the next 5 values. And in order to avoid an error, the number of elements in your source array needs to match that in your target array. Using the shape function, you can always query an array for its dimensionality. That's quite common. It has to do with Numpy and its way to store data. That's kind of a rect array where we have 25 elements, which is true. Overall, we have that many elements. This reshape was performed, but it has not affected our array, right? Before making sense of that, the variable still is this one-dimensional array. And if you then type array.shape, by the way, shape, you don't call it that way because it's not a method. If you call it that way with brackets, it will give you an error, type error. Tuple object is not callable. Shape is a tuple that the class Numpy array exposes. Again, you will make this mistake many times and eventually realize that that's how to call shape. So we have this one-dimensional array, and it's not yet a proper vector. It could not participate in calculating a dot product or something. Very often you will have these one-dimensional vectors, and you will need to transform them into proper, or these one-dimensional arrays, and we'll have to transform these into proper vectors, and that is what reshape is for. So we could reshape that into a proper vector, which is 25 by 1, and then calling shape again. Also shows us this proper dimensionality, and now we could calculate a dot product, for example, with a matrix that is 25 by whatever, 50 dimensions. Now it would work out. Previously, it would not work out. All right. There is the dot function, which calculates the inner product of two vectors, provided all matrices, provided the dimensions work out properly, as here with these little vectors W and V, both of which are 1 by 3. And we are also illustrating in the tutorial here a little bit of matrix vector multiplication, where we define a matrix A and a matrix B. The dimensionality works out natively. If you look at that, A is 3 by 1 and B is 1 by 3. So we can calculate a dot product. And then get our 1 by 3 result, which happens to be 16, 6, and 8. This is, well, what's the take home here? Obviously, if you want to do matrix multiplication, you have to make sure that the dimensions of your matrices and your vectors work out. You can transpose the data, you can reshape the data to ensure that they do, and then you have the function dot in order to calculate a scalar product. And trust me, we'll do that a lot. Okay. Last bit. We also can solve linear equations. Let's say we have an equation, a by x equals to b, a by x equals to b, and we need to find x. Here is a Numpy example how we can do that. So first we design some data. We create our matrix A. That facilitates some debugging. So it's 3 by 3, right? Then we have our vector B, which is 3 by 1. And to solve this system, well, we could, there are multiple ways, in fact. We could also find the inverse of A and then multiply everything with the inverse of A. That would work out, but in fact, we don't even need to go there because for a linear system of equations, there is a branch within Numpy. Note this syntax here, np.linalg. There is a branch, linear algebra, where you have loads of functions that are somewhat related to one another or that come in handy for linear algebra. And there is solve, which allows us to solve the system a times x equals b. And then you find your result. And as a little bit of homework, maybe, because we made it all the way to the end for our first session, try to solve that using the inversion of A and then a matrix multiplication. That's a good little exercise. I know it was enough. It was a lot for start. What you've seen are many examples of Python syntax. You haven't seen any functionality that would have been new to you. All what we did as well in beds, and maybe you've done that in other courses. There was no really interesting functionality here, I know that. But to get started, we need to, first of all, learn about some common programming statements and some common Numpy functionality, and that was my point for today. Thanks for now. We'll soon continue with another video in which we'll look into pandas, data frames, and also do some plottings. Till then, all the best and take care.